Ladies and gentlemen, we are back. Today we're going to be looking at solutions. In order to understand a solution, you have to know what a mixture is. So mixture, we've seen this term in other chapters previous to this, combination of two or more substances not chemically united in a no definite proportion by mass. Mixture may be made from any combination of solid, liquid, or gaseous substances. So sand and gravel is a mixture, just as sugar and water is a mixture. Eating sand and gravel is probably not nearly as much fun as eating sugar and water. A solution is a special type of mixture. It's defined as a homogeneous mixture of two or more substances dispersed in a sufficient quantity of dissolving medium. A solvent is the dissolving media. A solute is the item that is dissolved. Solute can either be solid, liquid, or gas, while a solvent is always assumed to be a liquid. So a solvent, any of the three states of matter. Don't worry about plasmas. A solvent is always assumed to be a liquid. The word homogeneous implies that the components or ingredients of the solution are so evenly distributed that any sample of the solution is a uniform composition. Okay? So we see heterogeneous versus homogeneous here. Everything looks even. Everything looks very, very even. The simplest solution has at least two components, a solvent and a solute. The solvent is the thing that does dissolving, while the solute is dissolved. The solvent is always present by the greater amount in weight. You always have more solvent than you will solute. Okay? If a solute can be readily dissolved and absorbed into a solvent, we call it a soluble solute. Salt crystals would be described as a soluble solute when placed in the presence of water, which is acting as a solvent. If it's not readily dissolved, the solute is insoluble. The same salt crystals might be described as insoluble if they are placed in alcohol. They will not blend as easily. And there are many types of solutions, and most solutions are classified according to how their components relate to one another. So an aqueous solution or aqueous solution. Pick one. I won't hear you say it, so I won't probably care. A solution in which water is the solvent. A tincture, a solution in which an alcohol is a solvent. Miscible, a solution of two mutually soluble liquids, water and alcohol. Immiscible, a solution of two mutually insoluble liquids, so water and oil. A suspension, a mixture of a solute and a solvent in which the size of the solute particles is greater than 100 nanometers. The particles of the solute in a suspension do not pass through filters or membranes. They're stuck on one side if they try to filter through. Milk of magnesia is an example of a suspension. A mixture of two insoluble liquids, one being dispersed throughout the other in small droplets. So an emulsion is like oil and vinegar. Okay, emulsions are very common in cuisine when you're cooking. Electrolytic solution, a solution containing solutes capable of conducting electricity. Inorganic acids, bases, and salts in water. Non-electrolytic, a solution containing solutes incapable of conducting electricity. Organic carbohydrates, lipids, and alcohols in water. A true solution, a homogeneous molecule mixture of two or more substances able to pass through semi-permeable membranes. The size of the solute particle is less than 1 nanometer. That would be important, okay? We saw that 100 or greater was one, less than 1 nanometer would be another. True solutions are solutions which contain a soluble crystalloid solute, appear clear and transparent, will not settle out over time, and will not be separated into their various components by passing through a filter. True solutions are often referred to as crystalloidal solutions. Well, they've been beating you to death with this term. What is a crystalloid? It's a substance which is crystalline in its anhydrous solid form. It's form without water, anhydrous, without water, and capable of passing through both filters and membranes when it is the soluble solute in solution. So sugar water, salt water, arterial fluids, once we put the stuff in, it's all together. If we ran it through a filter, we ran it through a membrane, we would not likely be able to separate the components. Colloidal solutions are a solution-like system in which the size of the solute particles is between 1 and 100. So we had suspensions, true solutions, and colloidal solutions. The particles of the colloidal solution are capable of passing through filters, but not membranes. You know how this is going to need to be a chart, okay? So make one. True solutions, colloidal solutions, and suspensions and their characteristics. Crystal solutions may be called colloidal emulsions or emulsoid. A colloid is a substance which is not crystalline in its anhydrous solid form, and although it can pass through a filter, cannot pass through a membrane. Okay, cannot pass through a membrane. Gelatin, blood plasma, lanolin are all examples of colloidal solutions. Colloidal solutions are solutions which contain a soluble colloid solute, appear to be cloudy or translucent, will not separate out over time, but cannot be separated by filtration. Okay? Just as there are a variety of solutions, there are a variety of ways to express solutions in terms of measurement. There are two main ways to do so: quantitative and qualitative measurement. The two quantitative measurements are ratio and percentage. When a solution is expressed in terms of ratio, a comparison is made between the number of parts of the solute and the total number of parts in the solution. A solution of laundry bleach and water might be expressed in a ratio of 1 to 10. This means 1 part bleach to 9 parts water. The 10 refers to the total number of parts of the solution. Okay? So when looking at a ratio, the first number is always going to be the number of how many parts you are dealing with, whether it is the solvent or the solute. The second number is always a total number of parts, whatever it might be. 1/3, 1/10, 2/9, whatever it might be. So if you have a ratio and it is asking you what the other thing is, so if it's asking you what would be the number of parts of water if things called for a 1/10 ratio, 1 being your solute, it's simple. Subtract the first from the second, and that'll give you the number of parts of the missing item. Ratio measurements are expressed in terms of parts per million when dealing with minute amounts of pollutants in large quantities of water, alcohol, air, blah, 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 blah. When used in reference to solutions, percentage is defined as the number of grams of a solute in 100 grams of solution. A solution of soluble formaldehyde in water may be expressed as a 37 gram of formaldehyde in 100 gram of solution. When the 37 is divided by the 100, we get a percent. The word index is defined as the number of grams of formaldehyde in 100 grams of solution. An index is a special word used in funeral service, and anyone outside of funeral service will have likely no idea what in God's green earth you're talking about. So be very cognizant of that. Index is something that we use in the industry that many chemists and just other non-practitioners have no idea what we're talking about. Qualitative measurement is a comparison of the relative amount of solute present in a volume of solvent rather than precise amounts. The two common qualitative measurements are saturated and unsaturated. Saturated solution is defined as a solution containing all of the solute the solvent is able to hold at a certain temperature and pressure. The saturation point of a solution is dependent upon the specific solute and solvent being mixed together. A saturated solution of salt and water contains 357 grams of salt per 1,000 milliliters of solution. This precise amount of salt, which can be dissolved in enough water to create 100 milliliters of solution, implies that any specific solute has an upper limit as to how much of it can be dissolved in a given amount of solvent. And this is called the solubility of the solute. Blah, blah, blah. Fancy way of saying that there's just a finite amount of stuff you can put in the stuff that's doing the dissolving, and then it can't take any more. Plain and simple. Solubility is the measure of how well those two substances mix with each other to produce that saturated solution. Solubility is variable. It's dependent on a bunch of factors. For soluble solids and liquid solutes, their solubility is directly proportional to the temperature of the solvent. Translated, as temperature goes up, so does the amount of solute which can be dissolved. An increase or decrease in pressure has little to no effect on the solubility of soluble liquids or solids. If you put stuff under pressure, it's not going to mix any better. For soluble gas solutes, the solubility is inversely proportional to the temperature of the solvent. As the temperature of the solvent rises, the amount of gas decreases that can be dissolved. The solubility of a soluble gas solute is very much proportional to the amount of pressure that is directed upon the solvent. So as the pressure goes up, you can actually force more gas into the solvent. An unsaturated solution, well, contains less of the solute that can be held under normal circumstances. And if we look at our salt solution, it's basically anything which holds less than what it's supposed to. When dealing with saturated and unsaturated, they are dependent upon solute and solvent outside factors like temperature and pressure. And it says here a saturated solution of boric acid in water is 5% acid, while a saturated solution of formaldehyde is 37% formaldehyde in water. Sometimes the words dilute and concentrated are used regarding saturated and unsaturated. Scientifically, they are not related. Okay, they are not related. A dilute solution is defined as the solution which is holding a relatively small amount of solute relative to what it could hold under normal circumstances, while a concentrated solution is defined as the solution which is containing a relatively large amount of solute relative to what it could actually hold. So we're not talking about limits. We're not talking about anything more than, hey, dilute could hold more. In concentrated, it's holding a relatively large amount, still may not be saturated or even supersaturated. It's just holding a larger amount. So it's easily possible for a solution to be either dilute or concentrated, but yet still not be saturated. Okay? Know the fine points of those definitions. That's important. When a soluble solute is placed in the presence of a compatible solvent, they begin to mix together almost automatically. In the case of inorganic acids, bases, salts, or oxides being placed in water, new substances are formed by hydrolysis and ionization processes. In the case of soluble organic substances being introduced into a watery solute, new products are formed by hydrolysis, but not ionization. Okay? Soluble organic substances, hydrolysis, not ionization. Inorganic acids, bases, or salts, hydrolysis and ionization. A phenomena called diffusion takes place when solutes are placed in the presence of solvents. Diffusion is defined as the movement of molecules or other particles in a solution from an area of greater concentration to an area of lesser concentration until uniform concentration is reached. The rate of diffusion of a solute is directly proportional to the temperature. The warmer the solute and/or solvent, the faster the solute will disperse itself throughout the solvent. The cooler the solute, the slower. The end result of diffusion is a homogeneous condition. Everything is equal. The rate of diffusion is also directly proportional to pressure, concentration, and agitation. So rate of diffusion is affected by just about anything you can do to the silly solution. The rate of diffusion of a solute is inversely proportional to the size of the molecule of the solute and or solvent. The larger the molecule of solute, the slower the diffusion. Now osmosis. Osmosis is the passage of pure solvent from a solution of lesser concentration to one of greater concentration when two solutions are separated by a semi-permeable membrane. Okay, passage of pure solvent from a solution of lesser concentration to one of greater concentration when the two solutions are separated by a semi-permeable membrane. We go back to diffusion. Notice the differences. Okay, no membrane. That's the big one. This movement of the solvent across the semi-permeable membrane will continue until the concentration of the solute and solvent on either side of the semi-permeable membrane are equal. When the equality of concentration of the two solutions is achieved, the two solutions are referred to as isotonic solutions. Prior to the achievement of both solutions being isotonic, one was hypotonic and the other was hypertonic. Okay? Look at the picture. This is extremely important. The hypotonic solution had less solute but more water. The hypertonic solution had more solute and less water. There's a membrane that separates them. And what ends up happening is the water automatically will flow this way in order to achieve an even distribution where the concentrations are equal. A hypotonic solution is defined as a solution having a lesser concentration of dissolved solute in the solution to which it is being compared. A hypertonic solution is defined as a solution having a greater concentration of dissolved solute than the solution to which it is being compared. The force being exerted by the dilute solution against the concentrated solution during osmosis is called the osmotic pressure. That is an important definition. In order to stop the natural osmosis of the pure solvent across the semi-permeable membrane, a force equal to the osmotic pressure must be exerted against the semi-permeable membrane from the concentrated solution side. For this reason, osmotic pressure is sometimes defined as the amount of pressure needed to stop osmosis. Embalmers utilize principles of osmosis, dialysis, and diffusion when we do our job. Arterial fluids are designed to be hypotonic to tissue fluids, so that arterial fluid will be allowed to enter into the various cells, tissues, and organs of the body. The osmosis principle is also demonstrated in the process of hemolysis, and the crenation of red blood cells. Okay, not creation, but crenation. Hemolysis is the swelling and bursting of a red blood cell when it is placed in the presence of a hypotonic solution, whereas crenation is the shrinking of a red blood cell when it is placed in the presence of a hypertonic solution. The last type of movement is called dialysis. I referenced it a second ago. Dialysis is the separation of crystalloidal and colloidal solutes in a complex solution by passing the solution through a semi-permeable membrane. The crystalloids can pass through the membrane, but the colloids cannot and are therefore filtered out of the solution by the semi-permeable membrane. Some arterial fluids are colloidal in nature. Therefore, it is assumed that the colloids accumulate outside the cell membrane where they attract and retain the water forced out of the cell by the introduction of the dehydrating formaldehyde. If one applies additional pressure to overcome the initial resistance of the colloids to pass through the membrane, the humectant enters into the cell by a process called ultrafiltration. You are essentially forcing them through the holes as best as you can. Folks, thank you for your attention. We will see you next time.